Hello everyone, and welcome to Statics. My name is Nelson Clements, and today I'll be discussing our Module 3 discussion post. For my first problem, I chose F3-1. This problem states, the crate has a weight of 550 pounds. Determine the force in each supporting cable. So, first thing I did was draw a free body diagram. Here we can see our center point A. From here, we drew each vector out in its respective directions, also including the 3-4-5 triangle and the given 30 degrees. Next, we have our mass hanging down here with the weight 550. Step 2 is to find our components. The first one I wanted to do was my AB vector. To get this, I needed the ABX component and the ABY component. Since it gave me 30 degrees, I simply multiplied the AB force times cosine of 30 to find ABX. And since this is our origin and we're moving to the left in the x direction, it will be a negative x. That'll be negative AB cosine 30 degrees. Next, we'll do the same thing for our y direction. ABY will then be equal to the AB force times the sine of 30 degrees. In a Cartesian form, it'll be AB is equal to negative AB cosine 30, comma, AB sine 30. Next, I chose to get our AC vector. To do this, I'm going to use the little included 3-4-5 triangle and model ours similar to that. This will give us the AC in the x direction as 4 over 5 times AC. ACY will then equal 3 over 5 times AC. In Cartesian form, that'll be AC is equal to 4 over 5 AC, comma, 3 over 5 AC. Next, I'm going to go ahead and get our AD vector. Our AD vector, as you can see, has no x components in either direction. So that'll be equal to 0. Then, since there's only two forces acting on it in the y direction, the AD in the y direction will be equal to negative W. In our Cartesian coordinates, that'll be AD is equal to 0, comma, negative W. Our next step in this problem will be to solve our equilibrium equations. The sum of forces in the x direction is equal to 0, thus putting it in static equilibrium. So I'll take the components in the x direction from each of the above, which will give me negative AB cosine 30 degrees plus 4 over 5 AC plus 0 equals 0. Since the AB cosine 30 degrees is negative, I'll go ahead and move him to the other side of the equal sign, giving us 4 over 5 AC is equal to AB cosine 30 degrees. After dividing by that cosine 30 degrees on each side, we get AB is equal to 4 over 5 AC divided by cosine of 30 degrees, and after typing that in the calculator, that gave me AB is equal to 0.9238 AC. Now, I'm going to move over to the sum of forces in the y direction. The sum of all forces in the y direction is equal to 0. So that means we'll take our y components from above, AB sine 30, plus our 3 over 5 AC, and then instead of putting the minus W, I moved that to the other side and went ahead and just put its value 550. This will give me AC times 0.9238 times sine 30 degrees plus 0.6 AC is equal to 550. Pulling the AC out of that and doing all that math there, we get 1.062 AC is equal to 550. Dividing that by the 1.062, that'll give us AC is equal to 517.9 pounds, and when rounded, that'll be 518 pounds. I know I put a square around this one and an arrow, but I lied. We're actually using this value today. So I'll take that 517.9 and I'll plug it into our previous equations that we found over here. replacing this AC. That'll give us AB is equal to 0.9238 times that 517.9. That'll give us AB is equal to 478.4 pounds, and when rounded, gives us AB equal to 478 pounds. That completes our equilibrium equations and solves the problem. Moving on, my next problem that I picked was F3-11. This states the 150-pound crate is supported by the cables AB, AC, and AD. Determine the tension in these wires. Just as before, our first step is a free body diagram. We're going to start at our center point here, A. As you can see, I made the point A right there, my center, all zeros. Then we drew our vectors coming off of it for C, B, and D. Also the weight hanging down on E. Now to get these vector values, I like to take the final point, for example B, and subtract it from the initial point, which is A. So taking B minus A, I got -6, 3, and 2. Now to get a unit vector for that, I put that over the square root of those values squared. So for our B vector, I got the values -6/7 FB, comma, 3/7 FB, comma, 2/7 FB. I repeated this process for our C values, which final minus initial gave me -6, -2, and 3. I put those over the square root of their squares added together, which gave me -6/7 FC, -2/7 FC, and 3/7 FC. Since the D value only acts in the X direction and not in the Y or Z, its value is simply D, 0, 0. The same goes for the crate hanging in the tension of E. It's only acting in the Z direction, which is -150. Moving on from there, for step 3, we'll find our equilibrium equations. Here, we set the sum of all forces in the X direction equal to 0. This gives us 0 equals -6/7 FB minus 6/7 FC plus FD. Moving these negatives to the opposite side of the equal sign, we get FD is equal to 6/7 FB plus 6/7 FC. Next, I'm going to go ahead and move over to the sum of all forces in the Y direction equal to 0. This gives us 0 is equal to 3/7 FB minus 2/7 FC. Since the 2/7 FC is negative, I moved it to the other side of the equal sign. This gives us 2/7 FC is equal to 3/7 FB. I went ahead and did some calculations on these fractions to get some decimal values. Then I subtracted the decimal value with the FC from both sides of the equal sign. This gives me FC is equal to 1.5 FB. From here, I'm going to move up to the sum of all forces in the Z direction. This will give us 2/7 FB plus 3/7 FC minus that 150 pounds will equal 0. After doing some calculations on these values and moving this -150 to the other side, we get 0.2857 FB plus 0.4286 FC equals 150. Now, since we just got a value for FC, we went ahead and plugged that in here. This gives us only one unknown variable. That way we can solve for it. Doing so gave us 0.9286 FB is equal to 150. Dividing by 0.9286 on either side of the equal sign gives us FB is equal to 161.5 pounds. When rounded, FB equals 162 pounds. From here, we're going to take this FB value and we're going to substitute it in right there. Pretty easy. That'll give us FC is equal to 1.5 times 161.5, or FC is equal to 242.3 pounds. Now, since we have both our FB and our FC values, we'll go back over here and calculate our FD value. Substituting in for the equation above, we'll get 6 over 7 times 161.5 plus 6 over 7 times 242.3. This gives us FD is equal to 346.1 pounds, or when rounded, FD is equal to 346 pounds. That solves the equilibrium equations and gives us the tension in each of these cables above.